Hello everyone. In this tutorial session, we will try to solve some problems in relation to block diagrams and signal flow graphs that we have studied in the previous classes. So, to begin with, we will try to draw a simple control system with a plant and a feedback loop. So, this is how the block diagram looks like. So, this is the input u, which goes with a positive sign into this, and this is a control system with transfer function c, and then we are adding a disturbance signal along with the control signal, both we take with positive sign, and then we have the plant with the transfer function g, and we also have a feedback loop with transfer function h, and this is the output. And just note that for the sake of simplicity, we are just ignoring the Laplace thing, but everything is in Laplace domain. So, these are in fact C of s, G of s and H of s, which we are representing as C, H and G for the sake of simplicity. So, what we will try to do here is, we will try to find the transfer function. So, here transfer function, there are actually two input signals that you have to notice. One is the normal input signal that you know, and there is another disturbance signal which you do not know. So, we can find the transfer function both with respect to both these inputs. So, that is, we can find out what is y of s by u of s, and then we can also find out y of s by d of s. So, not only finding the transfer function, what we will do is, we will try to show that y of s is actually a response due to the input and the disturbance when they act individually while the other is completely 0. So, while doing this, what we do is, while finding out this transfer function, we will make d 0, and while finding out this transfer function, we will make u 0, and then finally we will try to find out the overall transfer function using superposition. So, as these are parts, I will call them y1 and y2. So, this is y1 is the response when u alone is acting, and y2 is the response when d alone is acting. Now, so to find out y1 by u1, we make this 0, and so our block diagram changes. So, this part goes off completely, and no sorry, y1 by u1 we make d 0. So, this part goes off completely, and what I will be remaining with is something like this. So, we are taking a negative feedback. So, this is y1. Now, this is a very simple feedback loop, and we know the transfer function of it directly. So, y1 by u is nothing but the forward loop transfer function c into g by 1 plus c into g into h, the feedback transfer function. Now, what we will do is, for the sake of simplicity, we will even take h is equals to 1. So, then our transfer function becomes c g by 1 plus c g. Okay. So, this is 1. Now, you will find the other transfer function by making this 0. So, when we make that 0, we get a diagram like this. put this as C, and because it is a negative feedback I will take it as minus H. So, C and H go into the same loop because this completely vanishes, and now this is y 2. So, again this is a feedback loop, and we can take the transfer function to be y 2 by d is equals to g by 1 plus g c h, right. Now, as we took h to be 1, we can just write it as g by 1 plus g c. So, this is my second transfer function. Now, my overall response y can be actually written as y 1 plus y 2 by principle of superposition. And so, if I take y 1 plus y 2, which will be, so y 1 is u times C g by 1 plus C g plus d times g by 1 plus C g. So, this is nothing but u C g plus d g by 1 plus C g. So, that is the overall response of the system. Now, if we even do the same thing normally, if you take the complete system and try to find the overall response, that is what you will be getting. So, this is a kind of verification of the superposition principle using this block diagram. Now, what we will do is, we will take up a slightly complex block diagram of a system and then try to find its transfer function, and then we will convert the block diagram into a signal flow graph, and then we will again find the transfer function. So, we will have a comparison of how difficult it is to find the transfer function using the block diagram directly and then using the signal flow graph using the Mason gain formula. So, this is the block diagram that we take. So, as you can see, this is a pretty much complicated block diagram, and it has about 1, 2, 3, 4, 5, 6, 7 and 8 blocks. Each block has its own transfer function, and you can see there are 3 feedback loops and 1 parallel combination as well. Now what we will do is we will simplify this block diagram using the rules of block diagram algebra. And so how do we begin with? The first thing you can observe is this is a feedback loop which we can easily simplify. This is a parallel and this is also another feedback loop, but there is a small complication here. So this point and this point are slightly off positions for us to easily apply the feedback formula that we know. So what we can do is we can shift this here, and once we shift that, we can easily find out or simplify these blocks and find out their overall transfer function. So once we transfer that block, this is what we get. So I will only draw this part of the transfer of the block diagram and see how it looks like once we shift that. So once I shift that, the point comes here, but for shifting that there is something which we need to compensate. If you look at here, what is the signal that is coming out? Whatever the say, if I call this has the signal at this point as A, so the signal here will be A times G3. Now if I shift this from here to here, I will be getting only A. I will be losing out on this G3. So what I will do is I will put it here, H2 times G3. So this whatever I lost, this gain by shifting this point to here, I will be compensating it by including it in the feedback transfer function. So this transfer function is now H2 G3 and everything else remains the same. So now we have a simple kind of a diagram, this point here and this thing. So what we will do is we will apply the rules that we already know. We will find out the transfer function of this block and this block. So this will be G4 by 1 plus G4 H1, and this will be just the summation G3 plus G5, and this will be G2 by 1 plus G2 H2. Now once I do this, I can redraw my whole block diagram in a much simpler fashion, which is looking like this. So this will be G2 and G3 as H2 and G3, because this G3 got multiplied here when we shifted this point. So, this is how the simplified block diagram looks like. So, we just have G1 coming here and this reduction going into G2 by 1 plus G2 G3 H2 and this parallel block going as G3 plus G5 and this feedback loop going as G4 by 1 plus G4 H1. So, now we have two more simplifications to do. One is the cascade of all these 4 blocks and then applying the feedback law, right. So, once I apply that, so the cascade thing will be something like this: G1 times G2 by 1 plus G2 G3 H2 times G3 plus G5 times G4 by 1 plus G4 H1. So, this will be in a single block now. I can just add a unity feedback to this. So, now I have a very simple feedback loop and I can apply the feedback loop formula and get the transfer function. So, the overall transfer function will be like this. So, I am doing all the simplification and then giving you the final answer. You can do the simplification yourself and check. So, this will be the overall transfer function of the system. So, that is what we did was we started with a very complicated block diagram and then we used the rules that we already studied in the previous class and tried to simplify the whole block diagram and finally arrived at the transfer function. Now, what we will do is we will draw this block diagram in terms of its signal flow graph and derive the same thing and see if both are equal or not. So, this is how the signal flow graph looks like. So, while converting a block diagram to signal flow graph, one should be very careful to ensure that some branches are not missed out like this. So, when you go from G3 to G5, there is one takeoff point followed by a summer, and so you cannot take it to be one node. So, every takeoff point and every summer should have its own node, and because there is no gain over this, we will take a gain of 1. So, similarly, when you write negative feedback, you should ensure that you put the minus sign here, because there is no summer kind of thing in the signal flow graph, the negative sign goes into the gain. And this we was discussed in the class, that you should add a branch to ensure that your input and output are as per the defined, as per their definitions. So, now this is how the signal flow graph looks like, and now what we will do is we will apply Mason's gain formula and try to derive the transfer function. So, to begin with, so what are the forward paths? One clear forward path is from u to y. When we go, we have G1, G2, G3, G4. Another forward path is G1, G2, G5, G4 and y. And so, there are no other forward paths. So, this graph has only 2 forward paths. Now, what about the loops? One loop is this. So, and another loop is G2, G3 minus H2. And another loop is G1, G2, G3, G4 with unity feedback. And you should be careful that there is also another loop with G5, that is G1, G2, G5, G4 with negative feedback. So, generally people miss out on this, so we should be careful here. So, now we have the forward paths and the loops. Now, we will go to the non-touching loops. So, out of 4 loops, if you look at these 2 loops, these are not touching each other, they do not have any common nodes or branches. So, among the non-touching loops we have L1, L2 and G2, G3, G4, H1, H2. And if you observe, there are no other non-touching loops, because this loop and this loop are touching, this and this is touching, and even with G5 these 3 are touching each other. So, there are no other non-touching loops, and if you even go to 3 non-touching loops, there is nothing, there are no 3 loops which are not touching. So, this is where we stop. Now, we all have all the required components to substitute in the Mason's gain formula. So, we looked at the Mason's gain formula giving us the transfer function is given by sigma k is equals to 1 to n p k delta k over delta. So, now we know both p k, and before going to delta k we need what is delta. So, we will define what is delta. delta is, as per the definition, it is 1 minus the sum of individual loops. So, I will take a plus sign because all of them have a negative and I can simply add them up. So, these are all the individual loops plus the products of the non touching loops. So, we have only one set of non touching loops, I will just add it here. So, this is delta. So, what about delta 1? So, if I take the first forward path, there is no loop that is actually not touching that forward path. So, my delta 1 is simply 1, and even if I take the second forward path, this case is the same. So, my delta 2 is also equals to 1. Now, I can simply substitute everything into this Mason's gain formula, and what I will be getting is the same transfer function. So, you can simply observe this delta is nothing but the denominator which we got here, and if you just add up the forward paths, it is nothing but the numerator that we got, because delta k is 1 in both the cases. So, this is how you got the transfer function in both the cases. And the most important point to note here is, when you have a signal flow graph, it is actually very easy to derive the transfer function. In this case, you have to do lots of computations, lot of simplifications, and before you could arrive this at this transfer function, but here it is very simple. And even if there are more complicated block diagrams, it is always observed that signal flow graph does very well in finding out the transfer function. So, that is the advantage here. And now, for the last problem of this tutorial, we will try to find out a signal flow graph from a network directly. So, we were told that apart from finding out from the block diagram, we can also find out the signal flow graph from the network equations, and that is what we will try to do in the next problem. So, I will take a network with some RLC components. So, this is the network that I am taking. I have an input source V I, 2 resistors R1 and R2, and 1 capacitor C and an inductor L, and our output variable is, we defined it as the voltage across the resistor R2. So, here I will take the branch currents to be I1 and this branch current to be I2. So, this will be simply I1 minus I2. So, we will be dealing with these variables. So, first what we will do is, we will write down the equations based on the Kirchhoff's laws that we know. And so, the voltage here also I am defining it as V1. So, this will be anywhere V0. So, what is my Vi of S? I am directly writing everything in Laplace domain, because now we are comfortable with writing down network equations in S domain directly. So, my Vi of S is nothing but R1 times I1 of S plus V1 of S. So, this is equals to this plus this, and my V1 of S, I can write it as 1 by SC times I1 of S minus I2 of S. And V naught of S can be written as R2 times I2 of S. So, we have these three equations. Now, while drawing the signal flow graph, you have to go from Vi to V naught. So, in between, as we said, the nodes are actually the system variables. So, we include all these variables as nodes I1, I2. So, the easiest way to do it is always put it in the order in which they appear in the series circuit. So, it is I1, V1, I2 and V naught. So, okay, first I will put I1, okay, V1, I2 and V naught. So, again everything is in S domain, we are just using the variables directly without representing S. So, how do we connect these nodes using the signal flow graph? As we said, we are using the equations to find out what will be the signal flow graph. So, I have certain equations which relate these variables. Now, I need to find the right gains which will connect these things. So, firstly, what is the connection between Vi and I1? So, Vi is nothing but R1 times I1 . Okay, so because I will be writing I1 in terms of Vi, I need to reconvert this equation first. So, what is I1 of S? It is nothing but Vi minus V1 divided by R1, right. So, my I1 is depending on Vi and V1. So, what is the factor with which it is depending on Vi is 1 by R1. So, my gain on this will be 1 by R1, and with a negative 1 by R1 it is depending on V1. So, I will write it as feedback. Because this is appearing after I1, I will put it as a feedback. Okay. So, now what is the relation between I1 and V1? So, we know that V1 is I1 minus I2 by SC, right. So, V1 is depending on I1 with a factor 1 over SC, and it is depending on I2 with a factor of minus 1 by SC. So, I will put minus 1 by SC. Now, what is the relation of I2 and V1? So, we already know this relation. What we will do is, we can take another relation as well, which will actually give us a nicer this thing. We will take V1 to be Ls times I2 of S plus V naught. This is fine, right? I can because this is current I2 and this is an inductor, I can write it as L times S into I2 of S plus the voltage here, which is V naught. So, why did I write it in this fashion? Because I have to observe that in the nodes I took, I2 is appearing between V1 and V naught. So, it will be easy to draw the signal flow graph if I have I2 in terms of V1 and V naught, right. So, what is I2 in terms of V1 and V naught? One by Ls terms V1 of S minus V naught of S. Okay. So, I2 is depending on V1 with a factor 1 by Ls. So, I can simply connect this, and it is depending on V naught with a factor minus 1 by Ls. Now, finally, what is V naught? V naught is simply R2 times I2. I can simply write R2 here. So, my V naught will be simply R2 times I2. Now, if you look at the signal flow graph, this will exactly represent all the equations that we have written here, and so there is nothing that is missing. The complete network is actually coming into this signal flow graph. So, now what we will do is we will try to find out the transfer function. Earlier we used to apply all this thing and do elimination and find out the transfer function. Now, because we have a signal flow graph, we can apply Mason's gain formula and find out what is the transfer function. So, as you can see, there is only one forward path here and its gain is 1 over S square times R1. This is R2 is on the top, R1 L and C. So, this is my forward path gain. And then what about the loops? I have 3 loops here, right. One is minus 1 by S R1 C, this loop. I have another loop which is minus 1 by S square L C, and the third loop is minus R by R2 by SL, right. So, we have 3 loops and 1 forward path. So, what are the non-touching loops? So, these two are touching, these two are touching, but this and this are not touching. So, I can write L1 L3, which is R2 by S square R1 LC. Okay. So, now simply we apply the Mason's gain formula to get the overall transfer function, which is okay. Before the Mason's gain, we also need to find out what is delta. So, I will write down what is delta here. 1 minus, so because everything has a minus, I will put a plus 1 by SR1C plus 1 by S square LC plus R2 by SL plus this one R2 by S square R1 LC. Okay. So, this is my delta. Now, once we have, and what about delta 1? delta 1 should be 1 because there is no loop which is actually not touching the forward path. So, when you go from here to here, every loop is being touched. So, delta 1 is 1. So, what will be the overall transfer function is simply P1 delta 1 by delta, which is nothing but this is P1 divided by this whole delta. So, that will give you, you can just simplify it and find out the overall transfer function. So, instead of doing all the analysis and trying to eliminate everything and finding out what is V naught by Vi, we can simply draw the signal flow graph and directly get the transfer function. So, that is it for the tutorial today. Thank you.